Hi class, I just wanted to offer some help here for this project, just in case anybody's still struggling with it or needs some advice. Well, part 1A asks us here to draw a free body diagram. We have our truss here at the top, but we need to recognize first that we have a 2 kips, 2 kips, 2 kips, and 8 kip external load on the truss. So these 4 loads are drawn with force vectors at their specific locations. It's good to see that they're all parallel and coplanar. So we first need to draw ourselves a reference system here, a y and an x. Now, the reason we draw this reference system is so that we can reference these vectors and directions when we sum moments and sum the forces. We always say we're going to sum the forces in y, but sometimes we never put a coordinate system on there, so we don't know what the y direction is. Y is arbitrary and is usually, we draw it in the vertical direction, but you can actually angle a coordinate system any way you want. So this creates that communication through these drawings, is we know what y is and we know what positive x is, positive y, positive x. So for part A here, draw a free body diagram, is we need to replace anything that's touching our truss and these ground connections like at A and H, we need to replace them with reaction force vectors. And so your job for part 1A is to draw the truss here with none of those ground reaction connections, but in their place is going to be the force vector. So we should have what's equivalent of a pin in force vectors here and here. And then you always need to include your original external loads and their amounts here. Okay. Once you do that, once you find the correct vectors for A and H, point A and point H, then you can label them as like AY and AX or HY or whatever they may be. And then you need to solve for them in part B. And solving them is where we sum moments, is a quick way to get one of those force reaction vectors, get the magnitude, sum the moments about a point. So about some point equal to 0. And when I write this equation, oftentimes we couple it with a positive direction. So we're labeling that I am calling a rotation about this z axis that is coming straight out of the page at me, a positive rotation about z, I'm labeling that a positive direction. And that's how I keep my signs straight as well. So solve some of the moments about a certain point and you can get one of the reaction forces. And then you can sum the forces in y. And so when I say sum the forces of y, since I drew this coordinate system, I know what positive y direction is. Set those equal to 0, and I can solve the other reaction force. And then I can sum the forces in x equal to 0, and I know what a positive x is for my equation, and I can solve for that. So these diagrams, they create the communication. So if we're going to design this truss for somebody, we're going to figure out how much the walls need to hold. If this is our truss and these are external loads, well, the walls are going to be the ground reaction points, A and H, so the walls of the building. And so we need to know how much force is going to be on each wall at those locations if we load this truss externally in this way, 2 kips, 2 kips, 2 kips, and an 8 kips hanging load. All right, hopefully this helps. Hopefully this gives you a clue, but part A, I want to see this drawing without these ground pictures, no rollers, no pins, just force vectors. And part B, I want to see you solve some of the moments, some of the forces, X and Y, and give me the values for those reaction force vectors at A and H. Good luck.